In this lecture, I'll show you how to determine the electric potential. First, let's see the easy one, the potential due to a point charge Q as shown in the figure. According to this equation, if the electric field in space is known, we could calculate the potential difference between any 2 points A and B. As discussed earlier, at any point in space, the electric field due to a positive point charge Q is expressed by this equation, where R roof is a unit vector directed radially outward from the charge. To find the electric potential at a point located a distance r from the charge, let's begin with the calculation of the potential difference. We substitute vector E by this one. Because the magnitude of R roof is 1, the dot product of R roof and ds equals ds cosine theta, where theta is the angle between R roof and the vector ds. Please look at this figure. We found that ds cosine theta is the projection of ds onto r. Therefore, ds cosine theta equals dr. That is, any displacement ds along the path from A to B produces a change dr in the magnitude of R roof, which is the position factor of the point relative to the charge creating the field. Making these substitutions, we obtain the potential difference between point A and B as expressed by this equation. From this equation, what information could we have? It's noted that the line integral of the electric field is only dependent on the initial position and the final position. In other words, it's independent of the path taken between point A and B. If we multiply a charge Q0, the result is the work done by the electric force on the charge Q0 and is also independent of the path, which indicates that the electric field is conservative. We define a field that is related to a conservative force as a conservative field. Therefore, the line integral of the electric field of a closed path must be 0, as shown here. It's customary to choose the reference of the electrical potential for a point charge to be 0 at infinity. With this reference choice, the electrical potential due to a point charge Q at any distance r from the charge is expressed by this equation, V equals Ke Q over R. If there are 2 or more point charges, how to calculate the potential? Do you remember the superposition principle? The total electric potential at some point P due to several point charges is the sum of the potential due to the individual charges as shown here. Please note, this is the algebraic sum other than the vector sum. No need to consider the directions. We have known how to evaluate the electric potential due to a point charge and a group of individual charges. Then, how to calculate the potential due to a continuous charge distribution. Do you remember how to evaluate the electric field due to a continuous charge distribution? We divide a charged object into an infinite number of elements, each of which contains an amount of charge dq. dq could be modeled as a point charge. Here, we have the same way to figure out the electric potential due to a continuous charge distribution. The first step is to find a charge element dq. Then, we calculate the potential due to a charge element dq. The electric potential dV at some point P due to dq is calculated by this equation, where r is the distance from charge element dq to a point P. To obtain the total potential at P, we integrate dV to include the contributions from all elements of the charge distribution, as expressed by this equation. We could see that V equals 0 when P is infinitely far away from the source charge. Next, let me give you some examples. Please look at this figure. Here is a uniformly charged ring of a radius A and the total charge Q. Please find the electrical potential at a point P located on the perpendicular central axis of this charged ring. From this figure, we can find that the x-axis is perpendicular to the plane of the ring and its origin is the center of the ring. The symmetry of the situation tells us that all charges around the ring are equidistant from a point P. We apply the equation discussed earlier, substituting r by this one. Ke is a constant and can be moved from the integral sign. Noting that here, a and x keep constant for this integration, so they can also be removed from the integral. We integrate dq and obtain this expression. No vector consideration are unnecessary here because an electrical potential is a scalar quantity. Another example here. Here is a uniformly charged disk with a radius r and a surface charge density of sigma. P is along the perpendicular central axis of the disk. So, what's the electric potential at a point P? As we discussed earlier, the disk could be divided into many concentric rings of radius little r and width dr, with an area 2 pi r dr, as shown in the figure. Then we could employ our result for calculating the potential of a ring and sum the contributions of all rings making up the disk. We could find the amount of charge dq of radius r and width dr. Then find the potential due to the ring. Integrate dv over the limits from 0 to capital R. Finally, we have the potential at P. In some cases, if the electric field is already known from other approaches, such as Gauss's law, we could calculate the electrical potential due to continuous charge distribution by using the original approach. If the charge distribution has a high symmetry, we first find the electric field E using Gauss's law and then determine the potential difference delta V between any arbitrary 2 points. We then choose the electric potential V to be 0 at some convenient point and obtain the potential at some point. Let me give you an example. Please look at this figure. Here is a uniformly charged spherical surface with a radius of r. The total charge is Q. Please find the potential at a point A inside the surface and the potential at a point B outside the surface. Because of the symmetry of the situation, we could apply Gauss's law to find the electric field in space. Here are expressions for the field. According to the definition of the potential, we could calculate the potential by the line integral of the electric field. The potential at some point is equal to the work on the unit positive charge by the electric force by moving this charge from this point to infinity. So, for point A inside the surface, lowercase r is smaller than uppercase R. The potential at A is equal to the line integral of E over the limits from lowercase r to infinity. But please note that the electric field inside the surface is different from the one outside surface. So, here we have two items. The first item is the integral over the limits from lowercase r to uppercase R. And the second item is the integral over the limits from uppercase R to infinity. The first item is equal to 0, since the electric field is 0 inside the surface. Hence, we have this expression for the potential inside the surface. Then, how about the potential outside surface? The potential is equal to the line integral of E over limits from lowercase r to infinity. But in this case, lowercase r is larger than radius of the surface. So, the electric field keeps the same for this integration. Then, we have this expression for the potential of the region outside surface. This figure shows a plot for the potential as a function of R. It's noted that the potential is constant in the region inside the surface, while it's inversely proportional to R outside the surface. This example showed us how to calculate the potential if the electric field is given. What if the situation is reversed? I'll talk about it next lecture.